Hey everyone, welcome back. In this video, we're going to continue our discussion on chapter 3, and we're going to talk about some of the statistical tools that we could use the mean and standard deviation together. We will learn how to compute the coefficient of variation, and then next, we're going to talk about the empirical rule and Chebyshev's theorem. Then we're going to wrap it up to learn how to compute the z-score and standardizing data. So let's get started. Recall in prior videos, we learned about the mean and standard deviation. The mean is a measure of center and location, whereas the standard deviation is a measure of variation. Together, this allows us to calculate the coefficient of variation. So this is a ratio of the standard deviation to the mean, and it's always expressed as a percentage. It essentially shows us the variation relative to the mean, and we can use it to compare two or more data sets that are measured in different units. So here we have the formulas, and you notice that the population coefficient of variation and the sample coefficient of variation are very similar in structure. The only difference is the Greek letters that are used, which helps us understand if we are dealing with a population or sample. So whether you're computing the coefficient of variation for a population or a sample, it's pretty much the same process. We will first take the standard deviation and divide it by the mean, and then we're going to multiply by 100. So don't forget to include that percentage sign at the end so you know that you're dealing with a percentage. So let's go ahead and take a look at an example. So in problem 3.50 from the textbook, you're given the following parameters for two populations. In part A, we want to first compute the coefficient of variation for each population or each group. So first, we're going to plug in our standard deviation for our first population, which is 50, and then the denominator is 700. So 50 divided by 700 is 0.07, and then multiply by 100 to get 7%. So let's go ahead and do the same thing for population 2. So we're going to take our standard deviation of 5,000 and divide by our mean of 29,000, and we get 0.17, and then we multiply by 100 again, which gives us 17%. You can see that our data points are very different between these two populations, so that's why the coefficient of variation is so useful. Now, in part B, it asks us which population is more variable relative to the size of the population mean. A larger coefficient of variation means greater variability. We can now see that population 2 is more variable relative to the size of the population mean. So let's talk about the empirical rule and Tchebysheff's theorem next. The empirical rule is another useful rule to understand our data when our frequency distribution is bell-shaped. So if you recall in chapter 2, when we were calculating frequency distributions, some of them were shaped symmetrically like a bell. So according to the empirical rule, our population mean is in the center here. And if we go up one standard deviation and down one standard deviation, that means 68% of our data will fall within this range. If we go 2 standard deviations up from the mean and 2 standard deviations down from the mean, 95% of our data will fall within this range. Finally, if we go up 3 standard deviations and down 3 standard deviations, this virtually has all of our numbers in the dataset, or 99.7%. So anything beyond this would be extreme outliers. So let's look at an example how we could use this in practice. So imagine we have collected data on Uber rides in San Diego, and you're interested in seeing if it's worth becoming an Uber driver. The population mean is 15.1 miles, and the standard deviation is 3.1 miles per ride. So we're going to go ahead and plug in our mean and our standard deviation and calculate 15.1 plus 1 times 3.1, and then minus 1 times 3.1, and we get a range of 12 to 18.2 miles. We can expect that 68% of our rides will be somewhere between 12 and 18.2 miles. Now let's go ahead and go out 2 standard deviations. We're going to take 15.1 and calculate plus and minus 2 standard deviations, or 2 times 3.1. And now we get a range of 8.9 to 21.3. So going up 2 standard deviations will make our range wider, but now we'll cover 95% of our rides. We could use this information to estimate how many rides we could get in with 1 tank of gas. So Chebyshev's theorem is another useful rule of thumb like the empirical rule. Note though that the empirical rule is only used for bell-shaped distributions, meaning they're symmetrical. This theorem is primarily for non-bell-shaped distributions, so that means it could be skewed or curved in any direction. So regardless of how the data is distributed, at least 1 minus 1 divided by k squared of the values will fall within k standard deviations of the mean. So let's work this out a little bit. So assuming k equals 2, we'll take 2 squared, which is 4, and so 1 over 4 is 0.25. Therefore, 1 minus 0.25 equals 0.75. So therefore, we can apply this theorem and say that at least 75% of our data values are going to be within 2 standard deviations of the mean. At 3 standard deviations, it increases to 89% of our data. It is important to understand that this indicates it is at least this much, but could be more. So this is a general rule of thumb that we could apply to any distribution. Let's wrap this up and talk about standardizing data. So earlier, we used the coefficient of variation to compare 2 populations. So standardizing data values allows us to compare different things with different measures on a consistent scale or standardized scale. This is what we call our z-value or our z-score, and it represents the number of standard deviations a value is from the mean. So here are our z-score formulas. Again, you're going to notice that the process is similar for the population and a sample. In both formulas, x is the data value that we're working with, and then we're going to subtract it from the mean, and then we're going to divide by our standard deviation. So let's go ahead and walk through an example. So IQ scores have a distribution that's thought to be bell-shaped, with a mean equal to 100 and a standard deviation of 15. So suppose a person has an IQ of 121, and we want to calculate the standardized IQ for this person. So here's our formula again, and we're going to take 121, which is the value or IQ score that we're working with for this person, and then we're going to subtract the mean of 100, and then we're going to divide by the standard deviation of 15, and we get 1.4. So in other words, a person with an IQ of 121 is 1.4 standard deviations higher than our population mean IQ. This lets us compare this individual's score to the mean. So let's do some more practice. In question 3.53 from the textbook, you'll notice in this problem we're talking about samples, but the process is the same. We will take each of our x values minus the mean and divide by our standard deviation to get our z-scores. So in this example, our sample mean is 1,000 and the sample standard deviation is 250. So in A here, the x is 800. So we'll take our x of 800 minus our sample mean of 1,000. We will then divide by our standard deviation of 250, and we get a negative 0.80. So in other words, 800 is negative 0.8 standard deviations below the sample mean. So in B, our x value is 1,200. So plugging that into our formula, we'll take 1,200 minus 1,000 and divide it by 250, and we get 0.8. So you'll notice the mean and standard deviation did not change. The only thing that is changing is our x value. So in C, our x value is 1,000. So plugging that into the same formula, and we get 1,000 minus 1,000 and divide by 250, and we get 0. So our x value was the same as the sample mean, so we can say we're 0 standard deviations from the sample mean. Well, everyone, that wraps up this video covering the coefficient of variation, the empirical rule, Chebyshev's theorem, as well as standardizing data with z-scores. That also concludes our discussion on Chapter 3.